Given these two DAGs, which both compute reductions, which one is better? Now, the linear DAG has a sequential chain of dependencies, so it can never really use more than one processor at a time, other than the loads. The tree, by contrast, can use parallelism at every level. So the sequential DAG will take O of n time, whereas the tree-based DAG will take log n time. Now, intuitively, if I give you two DAGs and they both compute the same thing, then you generally prefer the one that has more parallelism. But is that the only thing you care about? Does anything else matter? I'm going to walk you through a formalism called work-span analysis. It will help you answer these and a number of other interesting questions. Given a DAG like this one, I will always ask you two questions about it. The first question is, how many vertices does it have in total? And I'm going to give this a name. I'm going to call it work. And I'll usually write it as W of n, since the total number of operations should somehow depend on the size of the input n. Now, computing the work is easy. You just count the number of vertices. The second thing I'll ask you about a DAG, always, is how long is the longest path through the DAG? This also has a special name. I'm going to call it the span. And I'm going to use the symbol d of n to represent the span. Now in this DAG, here is the longest path, which I've circled. And this path also has a special name. It's called the critical path. Now as a historical aside, the length of this critical path, or what I just called the span, historically was called depth. And that's why I'm using the symbol d of n. Back in my day, we didn't have no span. We called it depth, and you liked it. So in terms of work and span, can we now say something about the time to execute the DAG on a PRAM with P processors? Well, here are some simple things we can say. First, if all the operations have unit cost, then the time to execute this DAG using only one processor should be exactly the work, W of n. Now let's consider the other scenario. Suppose I give you an infinite number of processors. What's the time? Well, if you have an infinite number of processors, it really doesn't matter because you still have to execute the critical path. And that has length d of n. So the time given an infinite number of processors is d of n. So those are two handy facts, but I think we want to try to say more.